Hello students, welcome back to my channel. In this video, I am going to discuss in detail about the electronic configuration of elements up to atomic number 30. While writing electronic configuration, one should follow three basic principles, namely Aufbau's principle, Paulie's exclusion principle and Hund's principle. According to Aufbau's principle, electrons enters into the orbitals in the increasing order of their energy. Moiules diagram is highly useful to know the relative energies of various orbitals. Paulie's exclusion principles states that no two electrons in an atom can have same value for four quantum numbers. Two electrons may have same values for n, l, m, but they differ at spin quantum number value. So, in an orbital, the two electrons will have two opposite spins. Coming to the Hund's principle, whenever degenerate orbitals are available, degenerate orbitals means let us consider d orbital. So, d orbital consists of 5 subshells. So, these 5 are called as degenerate orbitals. So, whenever degenerate orbitals are available, then the pairing of electrons in these orbitals takes place when each orbital is filled with a single electron. For example, let us consider an element with D6 configuration. So, while writing D6 configuration, here these 5 orbitals are degenerated. So, we have to fill each orbital with the single electron. So, initially we will fill all the 5 orbitals with a single electron and then we will start pairing. So, here D6 electrons are available. So, the 6th electron will pair up the first orbital. So, in this way, whenever degenerate orbitals are available, we have to fill each orbital with a single electron, then only the pairing will start. So, these are the three basic principles. Based upon these three principles, one will write the electronic configuration. So, let us move on to the Moiules diagram. So, coming to the Moiules diagram, it explains the relative energies of various orbitals. So, while writing the relative energies of various orbitals, we have to know how many orbitals are present in each orbit. So, first orbit consists of only one s orbital. Coming to the second orbit, it consists of two orbitals, namely 2s and 2p. The third orbit consists of three orbitals, namely 3s, 3p, 3d. Fourth orbit consists of four orbitals like 4s, 4p, 4d, 4s, etc. So, initially we have to write the slanting lines and we have to start from right hand side to the left hand side while writing the slanting line. So, let us represent the slanting lines. So, this Moiules diagram is highly useful to know the relative energies of various orbitals. So, this is called as Moiules diagram, and from this diagram it is very clear we can predict the relative energies of various orbitals, and always we have to start from top to bottom and also from the right hand side to the left hand side. That means 1s orbital is having less energy than 2s and it is having less energy than 2p, than 3s, than 3p, than 4s, which is having less energy than 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, then 5d, then 6p, then 7s, etc. So in this way, it is possible to predict the relative energies of various orbitals. So while writing the electronic configuration, always an orbital with lower energy should be filled first. And coming to the capacity of various orbitals, here how many different orbitals are available? S, P, D, F. So what is the capacity of s orbital? Maximum it can accommodate 2 electrons. Coming to the p orbital, maximum it can accommodate 6 electrons. D orbital can accommodate maximum 10 electrons. F orbital can accommodate maximum 14 electrons. Is it clear about the Moiules diagram, students? Next, we will discuss about the electronic configuration of elements from atomic number 1 to 30. So, initially, let us discuss about the electronic configuration of elements from 1 to 14. Atomic number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So initially we have to identify the element with the corresponding atomic number. So if the atomic number is 1, the element is hydrogen and its symbol is H. Atomic number 2 means it is helium and the symbol is He. Atomic number 3 means the element is lithium and the symbol is Li. Atomic number 4 means the element is beryllium and the symbol is Be. Atomic number 5 means the element is boron and the symbol is B. Atomic number 6 means the element is carbon. Symbol is C. Atomic number 7 means the element is nitrogen and the symbol is N. Atomic number 8 means the element is oxygen and the symbol is O. Atomic number 9 means the element is fluorine and the symbol is F. Atomic number 10 means the element is neon and its symbol is Ne. Atomic number 11 means the element is sodium and the symbol is Na. Atomic number 12 means the element is magnesium and the symbol is Mg. Atomic number 13 means the element is aluminium and its symbol is Al. Atomic number 14 means the element is silicon and the symbol is Si. Let us see the configuration. So coming to the electronic configuration, hydrogen is having atomic number 1. So the first orbital is 1s and it is having only 1 electron. So 1s1. Helium 2, that means 1s2. And coming to the lithium, atomic number is 3. That means initially 1s orbital will be filled and then the electron goes to 2s1. And for that of beryllium, the configuration is 1s2, 2s2. Coming to the boron, its configuration is 1s2, 2s2, 2p1. Coming to the carbon, its configuration is 1s2, 2s2, 2p2. Students, always remember while writing the electronic configuration, we must follow NLX notation. N represents the principal quantum number, L represents the azimuthal quantum number, X represents the number of electrons. So coming to the nitrogen, its configuration is 1s2, 2s2, 2p3. And always remember that nitrogen is stable. Why? So coming to the last orbital configuration. So in the p orbital, 3 electrons are present. So according to Hund's principle, each degenerated orbital should be filled with a single electron. So in that case, here nitrogen is having half filled configuration, and hence this nitrogen is having stable configuration. So according to Hund's principle, an element with half filled or completely filled configuration is relatively stable. So nitrogen is stable according to Hund's principle. Coming to the oxygen, its configuration is 1s2, 2s2, 2p4. Fluorine, that is 1s2, 2s2, 2p5. And coming to the neon, it is the noble gas, and hence its configuration is 1s2, 2s2, 2p6. So what is the general configuration of noble gases? That is ns2, np6. So because of this stable octet configuration, noble gases are stable. They do not participate in chemical bond formation. And coming to the sodium, its configuration is 1s2, 2s2, 2p6 and 3s1. And it can also be written as up to 2p6. It is having neon configuration. So simply it can also be represented as neon configuration and 3s1. Okay students, and coming to the magnesium, its configuration is 1s2, 2s2, 2p6, 3s2, and hence it can also be written as neon 3s2. Coming to the aluminum, its configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So it can also be written as neon 3s2, 3p1. And coming to the silicon, its configuration is 1s2, 2s2, 2p6, 3s2, 3p2, and hence it can be written as neon 3s2, 3p2. Students, is it clear about the electronic configuration of elements up to atomic number 14? Next, we will discuss about the remaining elements. So, atomic number 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 and 26. So coming to the atomic number 15, the element is phosphorus and its symbol is P. And coming to the 16, so if the atomic number is 16, the element is sulfur and its symbol is S. Next, coming to the atomic number 17, the element is chlorine and its symbol is Cl. Coming to the atomic number 18, its element is argon and the symbol is Ar. If the atomic number is 19, then the element is potassium, and its symbol is K. If the atomic number is 20, the element is calcium. I think you are familiar up to atomic number 20. So coming to the 21, you just pay more attention. So coming to the atomic number 21, the element is called as scandium and its symbol is Sc. If the atomic number is 22, the element is called as titanium and it can be represented as Ti. If the atomic number is 23, the element is called vanadium and the symbol is V. If the atomic number is 24, the element is chromium and the symbol is Cr. If the atomic number is 25, the element is called as manganese and the element is represented by the symbol Mn. And if the atomic number is 26, the element is iron and its symbol is Fe. Is it clear, students? So, if the atomic number is 15, the element is called as phosphorus and its configuration is 1s2, 2s2, 2p6, 3s2, 3p3. Again here the p orbital is having half filled configuration and hence phosphorus is more stable and it can also be represented as neon 3s2, 3p3. Clear, students? Next coming to the sulfur, it can be represented as 1s2, 2s2, 2p6, 3s2, 3p4 and it can also be represented as neon 3s2, 3p4. And coming to the chlorine, its configuration is 1s2, 2s2, 2p6, 3s2, 3p5 and it can also be represented as neon 3s2, 3p5. And coming to the argon, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Again, this argon is having noble gas configuration and hence it is stable. Clear, student? So, maximum how many electrons can be accommodated in the p orbital? 6 electrons. So, coming to the potassium, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Next one is 4s. So 4s1 and it can also be represented as argon 4s1. So we can represent the nearest noble gas configuration followed by the remaining electrons. Clear, students? And coming to the calcium, it can be represented as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and it can also be represented as argon 4s2. Clear, students? It is the configuration of calcium. And coming to the scandium, here the next electron enters into the 3d orbital. Remember, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and then the differentiating electron enters into the 3d orbital. So remember, students, 4s orbital is having less energy than 3d. So initially the electron enters into the 4s orbital. So after filling 4s orbital, then the differentiating electron enters into the 3d orbital. Clear, students? So it can also be represented as argon 4s2, 3d1. And coming to the titanium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. And it can also be represented as argon 4s2, 3d2. And coming to the vanadium, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. And it can also be represented as argon 4s2, 3d3. And coming to the chromium, the configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6. And here you just try to write the configuration of chromium. So from vanadium, vanadium is having 3d3 configuration. So what we are expecting for the chromium? It may have 3d4 configuration. But almost 4s and 3d orbitals are having same energy, and hence if one electron jumps from 4s orbital to the 3d orbital, then what will be the configuration? It becomes 4s1 and 3d5. So remember, it is the anomalous behavior of chromium. So why chromium is showing anomalous behavior? Whenever the d orbital is half filled, it gains extra stability. Since 4s and 3d orbitals are having almost similar energy, to attain stability, the electron from 4s orbital jumps from 4s to 3d. Is it clear, students? So its configuration can also be represented as argon 4s1, 3d5. So the stability of chromium can be explained based upon the Hund's principle. So coming to the manganese, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Here again we have to fill 4s, 4s2, then 3d5. So it can also be represented as argon 4s2, 3d5. And coming to the iron, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And it can also be represented as argon 4s2, 3d6. Is it clear, students? Next, we will discuss about the remaining elements. So, if the atomic number is 27, then the element is cobalt and it can be represented as CO. If the atomic number is 28, the element is nickel and its configuration, its symbol is Ni. And if the atomic number is 29, the element is copper and its symbol is Cu. If the atomic number is 30, then the element is zinc and its symbol is Zn. Let us see the configuration. So coming to the cobalt configuration, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d7. It can also be represented as argon 4s2, 3d7. And coming to the nickel, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. And it can also be represented as argon 4s2, 3d8. Coming to the copper, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Here also, if the electron enters into the d orbital, we will get 3d9 configuration. And 4s and 3d are almost having the similar energy. So, one electron jumps from 4s orbital to 3d orbital. Then the configuration becomes 4s1, 3d10. So, the d orbital attains the completely filled configuration. With the result, copper gains extra stability. So, by following Hund's principle, both chromium and copper shows anomalous behavior to attain extra stability. So, its configuration can also be written as argon 4s1, 3d10. And coming to the zinc, Its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d10. Is it clear, students? So its configuration can also be written as argon 4s2 and 3d10. So always remember, students, the stability of nitrogen, phosphorus, chromium, copper can be explained on the basis of Hund's principle, and which states that elements with half filled and completely filled configuration are highly stable. So while writing the configuration, we will follow NLX notation. N represents principal quantum number, L represents azimuthal quantum number. So the maximum number of electrons that can be accommodated in the d orbital is 10. If you like the video, don't forget to share and subscribe. Thanks for watching.